of you have played tug of war. Sometimes a situation arises when your team and the opposing team are pulling the rope with full power. Yet the rope does not move in either of the directions. The same situation arises in the case of reversible reactions, where both products and reactants are reacting. But after some time, further change does not seem to be taking place. Observe these children playing balancing games. Both of these balancing games are examples of equilibrium. In the first case, the position of the stick remains constant. In the second case, however, balls are moving continuously, but there is always a ball in both the hands of the child. This is an illustration of dynamic equilibrium, in which the properties of the system remain constant, in spite of movement within the system. Consider a hypothetical reversible chemical reaction, where A plus B gives C. Let us introduce an equal number of A and B molecules into a reaction vessel. A and B combine to form C. Initially, due to their large presence, the molecules of A and B collide with each other rapidly, forming C. When the molecules of C are on the rise, the molecules of A and B are getting used up. This can be seen in the concentration versus time graph for this reaction, in which the concentrations of A and B are falling, while that of C is rising. However, we know that this reaction is reversible, and therefore the molecules of C start dissociating into A and B. This is what we call a backward reaction. Initially, the rate of backward reaction is slow because of the lesser number of C molecules in the vessel. However, the rate picks up as more and more C molecules are produced. Observe the system closely. The rate at which A and B combine to form C falls, while the rate at which C dissociates into A and B catches up. Graphically, the increase in the concentration of C now slows down, and so does the fall in the concentrations of A and B. After some time, when both the rates have become constant and corresponding to every molecule of C formed, a molecule of it splits into A and B. At this instant, the concentrations of A, B and C too become constant, and the system is said to have achieved equilibrium. Such an equilibrium in which the measurable properties of a system become constant in spite of an ongoing movement in the system is called a dynamic equilibrium. The constant concentrations of reactants and products are called their equilibrium concentrations, which remain intact until this equilibrium is disturbed. Clearly, the equilibrium concentration of reactants and products are not equal but constant. Let's summarize. We can conclude that a dynamic equilibrium is achieved in reversible chemical reactions occurring in closed systems, when the rates at which reactants combine to form products becomes equal to the rate at which products dissociate to give back the reactants. Whenever a system has achieved a state of dynamic equilibrium, the measurable properties of the system, such as the intensity as well as the concentration of reactants and products, becomes constant. It is very interesting that not only chemical processes but physical processes too have an equilibrium state. It is called physical equilibrium. For example, at 0 degrees Celsius, both water and ice are present together. To explore it more, watch our next video.
Keep imbibing. We believe in you.